Welcome to the course on power electronics with wide bandgap devices. Today I am discuss about static characteristics of any power devices. So static characteristic is important in order to find out maximum voltage, maximum current, on-state resistance, basically the static behavior of any particular devices. So in this process we have to provide pulsed kind of signal in order to get the static characteristics. Basically the static characteristics gives us IV characteristics of the device. So what are these IV characteristics? So basically it describes steady state behavior. So the first step to analyze any device is to find out the steady state behavior. So how the device will perform in steady state. So that is why this is very important, or this is the first step to understand any device. And they are very crucial to understand the device performance for fixed operating condition. If the operating condition changes, so obviously these characteristics will also change. So pulsed IV characterization uses a curve tracer for critical measurement. So generally for any device, in order to find out IV characteristics, curve tracer is required. So generally for silicon devices, these curve tracers are well established kind of equipment which people use often to characterize silicon devices. But these WBG devices, they are a bit different in terms of size of the devices, their parasitic parameters, their slew rate. All these things are much different from the silicon devices. So that is why in order to characterize the WBG devices, special kind of attention is required. So that is why I am going to discuss the static characterization in details and what are their requirements. Fundamental of pulsed IV testing. So what is this pulse IV testing? So whenever we need to characterize any device for the steady state behavior, so then the pulse kind of signal generally provided. So for in the curve tracer, this signal generally provided from the equipment itself. So we just need to place the device under test in the equipment and it provides all the signals automatically, and then it measures the signal output whatever is required for this characterization. But if in case we have to provide this signal separately, then we should have clear understanding of this signal and where exactly we should be providing. So in order to provide this pulsed kind of signal, so if we don't have the curve tracer, if we have to use the component whichever is available in the lab, and we have to make the setup using the component, so then the setup will look like, so it will need two different supplies. So supplies we can get from the lab. So the supply are basically get to source voltage and the drain to source voltage. How this drain to source voltage and get to source voltage looks like? So basically we need to provide step kind of voltages to both gate and the drain. So this, let's say this is the VDS we are providing. Now this will be connected to one current measurement port, so which will measure the drain current ID. Then this will be connected to one shunt resistance to limit the current, and it will also have one lead resistance connected in series. So this is lead resistance of the device, and this is shunt resistance to limit the current. Okay, now this will be connected to the device under test. So let's represent this as DUT. The full form of DUT is device under test. Now this will be connected to the negative terminal of the source. Now this device need to have also gate to source voltage, and this gate to source voltage will also be step in nature. In order to provide different get to source voltages, that is why we need to provide step kind of voltages. So then accordingly we can get the characteristics. Let's say for VGS, in case of silicon carbide device, it is varying from 0 to 15 volts. Then the step voltage should be provided such that in each voltage level, let's say 0 volts, 5 volts, 10 volts, 15 volts, we can characterize the output. Now this gate to source voltage is also connected to one current measurement port which measure the gate current and which is connected to gate resistance, and then this is again connected to the lead resistance of the device, and the negative terminal will be connected to this point. So this is the VGS and this provides the gate current. This is the gate resistance. One is gate resistance, one is lead resistance of the device. And here we can actually measure the voltage measurement of the device. It will give us actual drain to source voltage which is appearing across the device. Although we are providing drain to source voltage, but how it is appearing, so that we can get from this measurement. So this is the test setup for static characteristics. Okay, so if you have curve tracer which is easily accessible, then use the curve tracer. And if you can get if you can get suitable curve tracer for wide bandgap devices, that is wonderful. Otherwise you can actually use the same curve tracer which is used for silicon device and then modify it such that you can use it for wide bandgap device. And in case if you don't have any curve tracer available to you, then you can actually make your own setup, so which looks like this, and this you can use for characterization of the WBG devices or any devices you want to characterize. Okay, so now here you can see how this pulse signal should be provided. Now this pulse signal should be such that this is the test setup. So the pulse signal should look like, so it should have get to source voltage provided. So I am just showing you one signal, so there can be multiple signal provided at multiple voltage level. To give you the example, so this should be, let's say this get to source voltage we are providing like this. This is the get to source voltage which is having pulse width like this. Now when we are providing get to source voltage, then after that, after some delay point, the drain to source voltage needs to be provided. So if there is any dynamic situation or the condition which arise after providing the get to source, so that should reach to the steady state, then only the drain to source voltage need to be provided. So this is the drain to source voltage, and you can see here, so this is the delay between get to source voltage and the drain to source voltage. Now once we are providing drain to source voltage, so then there will be current flow from drain to source. So that current I have also shown in this test setup, so that is represented in terms of ID. So now let's say this ID we are getting like this. So now the measurement point of the ID should be at the middle point. So basically this is the delay for measurement of the drain current. So let me just point out. So this delay is required. This delay is required for providing the drain current, so that if there is any situation which is required get to, so that voltage across get to source, it should reach to the steady state value after, let's say, delay time, rise time, anything. So then this should first, get to source voltage should settle down, and then drain to source voltage should be applied. And once we are providing drain to source voltage, immediately there will be drain current. So then we should be able to measure that drain current, but we are not measuring drain current at this particular point. We are measuring drain current after some time, when it is reaching to the middle point. Because if there is any transient, let's say overshoot, undershoot, anything, any condition is occurring after providing the drain to source voltage, then what we have to do, we have to wait for some time, so that device will reach to the steady state value. Once it is reaching to the steady state value, then only we can actually characterize or measure this voltage across VDS and drain current, so that we can get actual steady state value, not the transient value. By default, if we choose the initial point, we may end up getting the transient values, so that may not be the actual value which we are desiring. So that is why we have to wait for some time in order to measure the drain current. So now this pulse width part is very important. You know why? Because once we are providing this pulse width, after, let's say, this delay time of the drain to source should be such that it generally like this should be provided based on the transient requirement, like when the device transient or the hard switching time will be over. So that delay time should be that much. And then this id current, when we are measuring, that should not be like the pulse width for that also should not be very high, because if we try to keep this pulse width very high, so then what will happen, this will end up increasing losses in the device. Because when the device is on, although we are actually neglecting the switching losses, but the conduction loss will increase, and that will increase the heat generation in the device. If heat is generated, so then what will happen, the device property will change. If the device property changes, then the static characteristics will also change. That I'll show you in characteristic curves how it will change. So that is why it is very important to keep this pulse width in optimum condition, so that we will not have the transient parameter, but we should be able to get the value of the steady state condition. Then we can actually keep that much pulse width, so which will give us steady state value, not more than that. Otherwise we'll end up actually measuring the value which may not be the value in the original condition due to increase in the temperature. Okay. So now this is as you have seen in the previous slide. So this circuit looks very simple, and also measurement looks simple, and also the pulse we need to provide, that is also only one pulse we are providing. So that should not be very much complicated, right? But there are challenges in characterization. So what are the challenges? So maintaining a device in an on state leads to conduction loss, as I told you. So basically we have to make sure that we are not increasing the conduction loss, and that optimum point we have to select. So that is one of the main challenges in static characterization. And obviously this loss will impact the junction temperature, and it will change the test condition. Let's say you are trying to achieve the condition at 25 degrees Celsius, let's say room temperature. Now if the test condition changes, so then what will happen, this 25 degrees Celsius can change to 50 degree or 100 degrees Celsius. Then you will not get the actual value. And third thing is that extended on-state period are difficult to manage in static test. So this is also another challenge. And then that is why the pulse test offer a solution of these challenges. So that is why this pulse kind of signal we need to provide. Okay. Now we have to focus in the middle part. As I told you, like after some delay time we can reach to the middle part of the current. So that part we need to focus in order to measure the actual static value. The transient at the pulse start are just a means to end after certain points. So we have to let go that transient part and we have to reach to the middle part. So after like few characterization you will be able to understand when this middle part is coming. So then you can choose the actual value. The middle pulse neglects the dynamic effect from the turn on and turn off transient. So this turn on and turn off transient we are not including in the static behavior. So here the main concern is the maximum voltage, maximum current rating of the device, what should be the on-state resistance, and what should be different current, basically the leakage current of the gate, leakage current of the drain, or the current flowing through the gate. So those current values will get. Okay. Avoiding hard switching helps reduce resonant energy and ringing. So basically if we have hard switching, so then that will cause some like resonating energy or the oscillation, and it will take some time to reach the steady state value. So that is why, like, if it is possible to avoid the hard switching by introducing soft switching, or providing the pulses such that it will like automatically go to zero, the current will go to zero. So then what will happen, then this resonating energy will not be there, then what will happen, the oscillation at the beginning will be much less. So then the reaching to the steady state situation will be much easier. Okay. Now techniques to the pulse testing. So this is like it can be applied to any device. So pulse testing, any testing, so they are common. So either static characteristics, dynamic characteristic, capacitive characteristic, any characteristics. So the characteristic should be common, like what are the things we need in the data sheet, but the method will change depending upon the device. So if the device is very sensitive, then we have to select a circuit or network which will not arise the additional parasitic parameter. So that thing we need to look into, but the parameter which whatever is required in the datasheet, they are like constant for all kind of devices. Let's say silicon MOSFETs and IGBTs. So whatever data are available in the datasheet, it should be the same for any wide bandgap devices. The difference in the sensitivity and measurement accuracy makes the difference. Silicon devices have higher thermal capacitor, allowing longer pulses, but you know the GaN silicon carbide, especially GaN, so it is having much lesser capacitance. So that is why the pulse width required for the GaN device should not be as wider as the silicon device. Again, the silicon carbide devices have having like capacitance level much lower than silicon, but bit higher than that of the GaN. So then the pulse width also be different. So that we need to find out like what should be the pulse width for different devices. So it should not be same for all the devices, silicon carbide and GaN. So and also like the small die size results in lower thermal capacitance. So that is also another important point when we are going to characterize this wide bandgap device. So and we are talking about different parameter, but till now we haven't discussed about junction capacitance, but this is like one of the important parameter. So this junction capacitance, it plays very important role for characterizing any device. So this pulse testing, it will affect, as I told you, it will affect the effect of this temperature in the device junction, so that we can assume that temperature will remain same as the beginning for characterization. Now precise control is very important in order to characterize the device, otherwise as I told you, the basically condition will alter. Whenever you see any data sheet, so they are generally given like what is the voltage current level, and additionally what is the junction temperature they have considered. So generally in the data sheet, so they take two different temperatures, one is the room temperature, another at a higher temperature, let's say 100 degrees Celsius. So you can see the parameter values changes as it goes from room temperature to higher temperature. So that is why they give two different temperature, and if it is possible to characterize the device for like multiple temperatures, so that is like much more advantageous. Then we can actually get the actual value depending on that particular temperature. Okay. So WBG devices are more sensitive to temperature changes than that of the silicon device. So this is like one another important point for WBG characterization. So this temperature we have to regulate properly so that we can get actual value in WG devices. Now, so till now you have seen this different IV and then junction temperature. Another important thing is the on-state resistance. Why it is important? So this is required for finding out the conduction loss. This is one of the important parameter in any device. So this pulse IV testing provides accurate this on-state resistance measurement as well. Okay, the lower the on-state resistance, obviously it is like better for any device, so the loss will be much less. So this is like very critical to evaluate the device performance and the efficiency level of the device. Then the maximum current capability. So the maximum current capability of the device is very important to find out the suitable device for any particular application. So pulse test also gives the maximum current which the device should be able to provide for reliable and safe operation. So this is also very important for any application. So this decides like maximum current level for which the device can be applied. Okay, and this now another thing is that the maximum voltage. Similarly, the maximum voltage. So first thing we notice in the data sheet is the what is the voltage and current level. So this also very important for to find out the breakdown voltage and ensure the reliability. This is also like very important for a particular application. Now, in this static characteristics, what are the different parameter we can get? So there are 4 different characteristics we can have using this method. So first is the output characteristics, which characterizes ITVDS. Second is the transfer characteristics. So this characterizes IDVGS. And third is the gate current characteristics. So what is the value of gate current with respect to different voltage at gate to source, that characteristic. And then fourth is the drain to source leakage characteristics. So this first characteristic is the ID versus VDS. So drain current with fixed gate voltage and varying drain to source voltage we can characterize by this method. So output characteristics: curve source, ohmic, saturation and body diode region. So reverse conduction varies with the gate voltage, should be characterized over a range of gate voltage and temperature. And on-state resistance also we can measure from this particular characteristics. Silicon carbide MOSFETs and GaN have unique on-state characteristics and require specific characterization method. So these are the different things which we can achieve in this particular characteristics. So let's see how this characteristics looks like. So when we are saying output characteristics, basically ID versus VDS, so then as I told you in the previous slide, the gate to source voltage is kept constant, right? So let's say first, so this first one characterize this ID and VDS with respect to different gate to source voltage. So let's consider positive VGS we are considering in this case. So now how this characteristics looks like? As I told you, we are characterizing the device, basically we are measuring the drain current with respect to, so it is positive, it is increasing in the positive direction, so with respect to different voltage level VDS. Okay, so VDS will increase from 0 to, let's say, maximum for 1000 volts, and drain current will increase, let's say, 0 to 100 amperes. So this is increasing like this, this is increasing like this. Now the important thing is that VGS need to be constant. Now VGS, if it is constant, so then let's say the characteristics looks like this. So VGS is constant, so this is let's say VGS equals to 5 volts. Now this, if I consider for silicon carbide device, now silicon carbide device we can have maximum get to source voltage 20 volts. So then if we try to increase this VGS, so then what will happen? This current will also increase. So let's say this is with respect to VGS equals to 10 volts, and then again it will increase with respect to, let's say, 20 volts. So this is how the characteristics will vary. So you can see here, so VDS as for any particular VGS, if we keep it either 5 volts or 10 volts, so then as the drain to source voltage is increasing, how the current curve looks like, that we can plot in this. In this case, very important thing is that junction temperature is constant. So in this particular this positive VGS we are keeping here, the important thing is that junction temperature Tj constant. Let's say Tj equals to 25 degrees Celsius. That is constant, that we are not varying, and we have to regulate that. That is also very important. If we are not varying, that doesn't mean that we cannot, we should not check that what is the junction temperature. We always have to maintain at 25 degrees Celsius. Otherwise, these characteristics will change. Now, this is with respect to silicon carbide device. Now, similarly, we can also plot for GaN device. It is also the similar thing. So ID we can plot here in the y-axis, and VDS it is in the x-axis. So similarly for ID, let's say for drain current it is 10 ampere maximum, and VDS let's say it is around 600 volts. It is increasing like this. Now get to source voltage for GaN it is different. So then VGS will also be different. So let's say after this is reaching to steady state, and then this is here VGS equals to 0. Similarly we can provide VGS, let's say it is equal to 2, VGS equal to 2. Now it is equals to 4. Okay, so this we can actually try to, so you can see here, so 10 ampere will be corresponding to 4. So like this we can actually plot different devices. So this is with respect to GaN. Okay, now you know that this get to source voltage here it is shown only positive, but in case of silicon carbide and GaN it is advisable to provide lower voltage in get to source as negative. Means in case of silicon it is like 0 to 15, means the voltage remains in the positive side, but in case of GaN and silicon carbide the voltage ranges can vary, let's say from -4 to 15 volts or -2 to +4 volts, like this. So this is this characteristics with respect to positive, but if we provide negative gate voltage, then how the characteristics will look like. So let's see that. So here also here we are providing negative VGS, and junction temperature we are keeping constant. Temperature TJ just a minute. TJ equals to 25 degrees Celsius as the previous one. Here we are actually considering negative voltage. So then negative voltage if we are considering, so then ID should be negative and VDS also should be negative. Now VDS, let's say it is varying from, VDS, it is varying, VDS here, it is varying from 0 to maximum of, let's say, minus 6 volts. And VGS, we are varying. So VGS, if we have to provide certain voltage, so let's say we start from 0 and then we go to the negative voltage level. So then the current level also will vary 0 to, let's say, minus 100 ampere. This is with respect to ID. So ID is increasing like minus 100 to 0 and VDS is increasing minus 6 to 0 volts. So VGS, if we consider some voltage level, let's say VGS equals to, initially it is providing, we are providing VGS equals to minus 2 volts. Similarly, if we provide VGS equals to minus 4 volts, similarly we can get sets of characteristics. This is with respect to the silicon carbide device. Now, if we consider the GaN device, we will also get similar kind of behavior. Now, GaN device, if we try to plot, so then what will happen? So similarly, we can get like VDS, it is like starting from 0 here, VDS, and it is going to maximum, not maximum, minimum minus 6 volts. So in this direction it is increasing, and current, it is like ID, so current level, it is starting from 0 here, and in this direction it is actually decreasing to minus 10 ampere. So this direction it is increasing. So now if I try to plot the characteristics by changing the gate to source voltage, so with respect to different gate to source voltage, the characteristics will be like this. So it will go like this. Okay, as the gate to source voltage will change, so it will change like this. So VGS will be, let's say, VGS will be equals to, let's say, here it is equals to minus 2, here it is equals to VGS equals to minus 3. So like this it can actually go to left side. So in this case it is actually going from like 0 to minus 2 in this case of silicon, and this is with respect to the GaN device. So this is how the characteristics will look like for positive and the negative gate voltage. Now, in these two conditions, temperature was constant parameter. But for any application, temperature may not be constant all the time. Actually, it is not constant all the time. Temperature will also vary, and also we can have a condition, or we can actually, if we certain application, we need to see the characteristics of the device at different temperature level, then we have to see the data sheet where the different temperature related characteristics is provided. If certain sets of characteristics is provided, from there we can actually get the required value. At least we can have the idea how the characteristics or how the values will change. So that is why now it is important to see how the characteristics will be for different temperature. Now I told you the circuit which you can actually develop in order to characterize the device. But if you have to provide the temperature, then what you have to do? You have to either use oven or the hot plate to provide the required temperature. Oven or hot plate, if you provide the temperature, if you set the temperature, it will give that temperature characteristics. Okay, so that you need to use if you want to get temperature related characteristics. Okay, so now let's consider this case. So in this case, temperature Tj is varying, VGS is constant. So we get ID versus VDS characteristics. So now how this characteristic will look like? We consider VGS is constant and positive. Okay, in this case VGS is positive. So now ID as it is varying, let's say 0 to 100. Similar device we are considering as the previous one. This this is V also varying 1000 volts days. Now let's say conditions we are considering Tj where it is varying from 25 degrees Celsius to 200 degrees Celsius. So we can have sets of characteristics, means one at 25 degrees Celsius, another at 50 degrees Celsius, another 75, then 100. Like this we can actually get the characteristics till 200. So how it will look like? So then the characteristics will look like, so basically it will have this kind of characteristics. So then it will actually, it will not vary much, means like this it will look like. So as the temperature is increasing Tj, so this different values will change, definitely change. Current and voltage values will change, but the variation will not be as much as it is with respect to VGS. So this is with respect to silicon carbide. And this one, let's say with respect to GaN. So we are taking the same device, same GaN device, let's say 0 to 600 volts VDS, and here it is varying from 0 to 10 ampere ID, and considering the same junction temperature condition, that is Tj varies from 25 degrees Celsius to 200 degrees Celsius. Okay, so then how it will vary? So it will vary like similarly like the previous case, but the variation will have slight change, not much change will be there. So with respect to temperature, different characteristics we will get. Okay, now this is Tj is varying, and then you are getting different characteristics of GaN and silicon carbide. This is with respect to GaN device. Sorry. Now we have the characteristics of the device, basically ID and VDS, with respect to different temperature and different gate to source voltage condition. Okay. Now how to find out on-state resistance, because on-state resistance will also come from this experiment, this different parameters only. So then if we try to find out on-state resistance, let's say on RDS on, so then how we can get? So this RDS on means it is having the information of ID and VDS. So this we can actually plot, and this will change with respect to temperature. Then junction temperature, with respect to that only we have to plot. So this is 0 and this is junction temperature, let's say maximum 200, that is what we have considered. And this RDS on, let's say for silicon carbide it is varying 0 to 140 ohm. So then how this is looks like? So another important parameter here will come, gate to source voltage. If gate to source voltage we are varying from 0 to, let's say 20 volts, positive voltage we are considering here, negative voltage we are not considering in this case, 0 to 20 volts. So then the characteristics will look like, so basically as the temperature will change, so then different characteristics will be like this. So like this the resistances will change. So in steady state, so basically after reaching certain temperature the resistance will be constant. Initially if we are considering 25 degrees Celsius, probably in that time the resistance will be much higher. As the temperature is increasing, resistance will go to the steady state value. It may be more or it may be less depending upon the gate voltage condition. So this is with respect to the silicon carbide device. This is for silicon carbide. And when we are considering the GaN device, so again the same parameter we are considering, Tj equals to 0 to 200 volts, sorry not 200 volts, 200 degrees Celsius, and here RDS on also we are getting. So in case of GaN, this RDS will be much lower. So basically here instead of considering 0 we can consider 25 degrees Celsius, because you know when we are considering this temperature, so the minimum temperature we can get room temperature here. Now this is, let's say, 120 ohm. So on-state resistance in this GaN, it is considered lower than that of the silicon. So here it is starting from, let's say, 60. So then the characteristics will look like this. So one thing you can see from here at least. So here also VGS is varying. VGS is varying from 0 to 4 volts, positive volts. So you can see as the temperature is increasing in case of GaN, so the on-state resistance is increasing. In case of silicon carbide, it is not like that. It is very different. So that is why this information we can get only if we characterize this. Otherwise, we get the constant value. In the datasheet, generally what they do, they give one value and also the electrical specification for that particular value is given. But if we want to select different specification, that we cannot get if we don't have this kind of characteristics. So that is why this kind of characteristic is very important. So now the second characteristic is the transfer characteristic. So what we get in transfer characteristics, we get ID VGS curve. So why it is required? So the drain voltage must be high enough to keep this device in the saturation region throughout the gate voltage range. So in this case we have to choose a condition, so where the drain to source voltage we have to apply, because in this case we will be varying VGS and we will be actually measuring ID, and here we can consider different temperature. But what should be the value of VDS? So for that what we have to consider, we have to consider a condition where VDS, just a minute, so I should use different color so that it will be visible. So VDS should be greater than VGS max minus VTH, threshold voltage of the gate. So this is the voltage we have to consider for this characteristic. Okay, the effective gate voltage should be chosen from the saturation region of the output characteristic. The transfer characteristic should exclude the ohmic portion and focus on the cutoff and the saturation region. Three key parameters identified from the curve, so that is the forward transconductance, threshold voltage and the Miller voltage. So this parameter is very important for designing gate driver for the device. So that is why this parameter we will get from this transfer characteristics, and this comes under static characteristic. These parameters are essential modeling of the device behavior and the dynamic characterization. We can design the gate driver from this characteristic, and also this is important for dynamic characterization. So that is why the static characteristic should come first. Once we have this information from the static characteristics, then only we can go for the dynamic characterization. Okay, so now let's see how this characteristic looks like. So we are considering this condition. So here if we want to characterize the silicon carbide device first, so the silicon carbide device, the VGS is varying, say let's say 0 to 10 volts, and now ID is varying 0 to let's say 100 ampere. Here then for different temperature we can consider junction temperature of the device, let's say 25 to 200. This condition we have used for the junction temperature. Then the characteristics will vary like this. Like this, the drain current will vary with respect to the gate to source voltage for silicon carbide device. Okay, the VDS already I mentioned how much should be the VDS, so that VDS we have to consider. Now for GaN device, we can choose the same device as the previous one. So the GaN device VGS obviously it will be much less than that of the silicon carbide device, so 0 to 4 volts, and obviously drain current will also be less, let's say 0 to 10 ampere. So then as the temperature is varying, TJ similarly it is varying from 25 to 200 degrees Celsius. So then the characteristics will vary like this. It will be constant for some time, then it will increase like this. Similarly, it will be constant for this time, and then it will increase like this. Then this, like this, it will change. Okay, so these are the different characteristics of the GaN device. So what are the things you will get? Miller voltage, threshold voltage, and then transconductance. So these are the parameters you will get from these characteristics. Now we have another important characteristics, that is gate current. So what should be the value of gate current with respect to VGS? As we are varying VGS, the gate current should also be variable. How it should look like? This we can actually get from this characteristic. So the gate leakage current, this is very critical for characterization, especially at temperature and voltage extreme points. So how much it will change, so that we need to know. The GaN FET may or may not have gate insulation. Sometimes we have insulated gate or like non-insulated gate in case of GaN, and some have intentional gate current for control. The gate current is influenced by temperature, gate voltage, drain current and voltage. Gate leakage current can be measured with a curved tracer or using a shunt resistor. So in the previous slide, so if you remember, I have shown one resistance. So this before this, actually you can see, I'm just going back to show you this resistance. So you can see here this shunt resistance. So this shunt resistance is used here. So this can be used to measure the gate current. So this is shunt resistance with respect to VDS. So here the gate resistance is placed. So this will give us IG. So basically this ID leakage current of the drain, it can be measured by this shunt resistance, and the gate current can be measured by this gate resistance. So this is what, this same setup we can use for this characterization as well. Okay, so now selection of the gate resistance, test lead length and gauge is very important in order to ensure the actual measurement. So now how this characteristics looks like? So in order to draw this characteristic, so this is with respect to the VGS. So we are considering non-insulated gate for GaN device. So GaN device we are measuring. So this is non-insulated gate. So then IG we can measure here. So it will be in milliampere, and it is varying, let's say from minus 10 to the power minus 3. So here it is varying from 0 to let's say 4 volts, 10 to the power minus 3 to 10 to the power 2 milliampere. So if the temperature, junction temperature is varying from 25 to 200 degrees Celsius, so how it will vary? It will vary like this. Initially some oscillation will be there, so then it will reach to the steady state value with respect to different temperature. This is for non-insulated gate. Now if I consider insulated gate, so then the voltage for the GAN device only, the insulated gate if I consider, so the voltage we can have higher range, let's say 0 to 10 volts VGS. And then similarly this is varying minus 10 to the power minus 3 milliampere to 10 to the power 2 milliampere. This is IG. Okay, so then this will vary like this with respect to different temperature. So it will vary like so. Here junction temperature similarly it is varying from 25 to 200 degree Celsius. Okay, this is with respect to gate current. Now another or the last characteristic which we can achieve from the static characteristics, that is drain source leakage current characteristics. So this drain to source leakage current measure the ID-VDS relationship with a fixed VGS. The test operates in the cutoff region and elevates VDS to above the device's voltage rating. Pulse testing is recommended to prevent the device damage or self-heating, as it is the requirement for static characterization. Gate voltage typically not pulse, sometimes shorted to the source. So the ID of VDS relationship is temperature dependent and varies with gate voltage. And leakage current generally increases with higher drain voltage. Okay, so then these characteristics, so basically if I have to show you the characteristics, so let me draw in the next slide. So here this drain characteristics, as I told you, so it is VDS will be varying, so that depends upon the device rating. Let's say 0 to 1000 volts for the silicon carbide device, same device we are using here. So this is increasing here, and then we have to consider one VGS. So like VGS should be constant in this case. So let me consider any value of VGS, any positive value of VGS greater than 0, and then ID it will vary. So here in this case ID will be microampere. So it is microampere. So the leakage current will be in microampere. So this will vary, let's say 10 to the power minus 3 to 10 to the power 1 microampere. So these characteristics, as the drain voltage is varying, if we haven't provided any gate voltage, since we are not providing the gate voltage, so gate terminal we can actually short it, means the drain to source voltage we are providing here VDS. Here with after this, like this device under test, we are providing drain to source voltage, device under test DUT. So then what we can do, we are not providing gate to source voltage, so gate to source voltage we can provide constant, or we can just short the gate terminal. Either VGS should be greater than equal to 0. We can provide 0 voltage also. How we can provide this 0 voltage? If we short this, okay, we are not providing any voltage, so then we can achieve this leakage current characteristics. So how it will look like? It will look like this. As the voltage is increasing, the leakage current value will increase. Okay, it will start from microampere. So that is very less. This is for silicon carbide device. And similarly for GAN device also you will get similar type of characteristics. It will also look the similarly. So basically 0 to 600 volts if I consider for GAN, and this will also be in the microampere range. So it is, let's say, minus 10 to the power 2 to 10 to the power 1. So it will be slightly different will be there. So it will be like this. This is for GAN. Okay. So this is how we can actually, you can get drain to source leakage current. and how it will vary with respect to different voltages. So these are the different characteristics you can see. Just a minute. Okay, this is repeat slide. Okay, so now you know. So this characteristic step different from for GAN, FET and MOSFET. Breakdown voltage is extracted by setting a current threshold. GAN FET do not have a clear breakdown voltage due to lack of avalanche breakdown. Manufacturer guidelines should be followed to avoid gradual dielectric breakdown in GAN device. The pulse setting should be balanced accuracy and device protection to prevent the self-heating and the damage for this particular characteristics. So okay, so these are the different characteristics you can get from the static characteristics. So ultimately what we achieve, so we know different things, we have different characteristics, we know the procedure for static characteristics, we know the basic things that we'll be achieving voltage, current and the drain to source resistance. So why we need this? So basically drain and gate leakage characteristics identify maximum voltage capabilities of the device. So this is the first thing we notice in the datasheet. Maximum voltage, how much it is, V max or V breakdown voltage. Output characteristics identify recommended operating current, so I max or I rated current. On-state resistance characteristics estimate the conduction loss. Conduction loss, so it gives us like what should be the loss during the conduction. So this is required for efficiency calculation. And on-state resistance curve helps to choose gate voltage current for gate driver design as well. This is very important because otherwise, I mean, like this dynamic characterization we won't be able to do using this gate driver. The transfer characteristics is important also to design the gate driver. This also indicates threshold voltage, Miller voltage, forward transconductance. Static IV curves provide input for dynamic characterization. So this parameter we get first and then we go for dynamic characterization. This is the reference for this particular lecture. Thank you.